Hello and welcome to the AP ECE Chemistry Chapter 13 Acids and Bases problem set with me, Mr. Wilkosz. Let's get started. Check out problem number 5. Problem number 5, you're asked to write the formula of the conjugate acid, and you're given a slew of different bases. Each substance has to have gained a proton compared to the original base formula, so it's gained an H+. So the charge should increase by 1 when we compare the base to the acid, and the formula should have an additional hydrogen when we compare the acid backwards to the base. And let's see if this holds true. In part A, OH has a negative charge, and the acid is 1 higher than that. H2O has an extra H as well. The hydrogen phosphate ion versus dihydrogen phosphate ion. Charge went up by 1. Number of protons, H pluses, increased by 1 as well. Ammonia versus ammonium. Charge went up by 1. Number of hydrogens went up by 1. Fluoride versus hydrogen fluoride or hydrofluoric acid. And then a complex ion containing waters and hydroxides, changing to contain 1 additional water, H2O3, and 1 less hydroxide, and the charge going up by 1. Take a look at problem 9, parts B and F. In problem 9, you're asked to use the Bronsted-Lowry model to show why the following would behave like weak acids and waters. You're giving the starting compounds here of a complex ion with aluminum and water, and you have to devise a way for it to look like it's acting like a weak acid. What happens is one of these waters donates one of its hydrogen ions to this other water over here, and so we get a hydronium ion, H3O+, and rather than having 6 waters conjugated with or complexed with the aluminum, we have 5, and then there's 1 hydroxide, that 6th piece, and then the charge is changed as well. Another complex ion with chromium, water, and hydroxide acting again here. We're like trying to show how it acts like a weak acid. We're going to have it donate 1 hydrogen, and so we're going to see this subscript 5 for the number of waters drop to 4. And we're going to see the number of hydroxides increase to 2, and the charge will also change. Check out problem 17, parts A and B. In problem 17, look at part A first, just specifically. You're given the hydrogen ion concentration. You're asked to fill out and find out what the hydroxide concentration would be, the pH, the POH, and then decide whether it's acidic or not. If we're given the hydrogen ion concentration, we can use the fact that the equilibrium constant for water, Kw, at 25 degrees Celsius is 1.0 times 10 to the negative 14th, and that's equal to the concentration of the hydrogen ion multiplied by the concentration of the hydroxide ion. So we can rearrange that and substitute in if we know the concentration of the hydrogen ion is 2.4 times 10 to the negative 8th, and we know that Kw is 1 times 10 to the negative 14th, we can solve out for hydroxide ion concentration as 4.2 times 10 to the negative 7th molar. pH is the negative log of the hydrogen ion concentration. Since we're given hydrogen ion concentration, it's just a matter of doing the mathematical operation, negative log, and we get a pH of 7.62. We can do 2 things now. We could do the negative log of the OH concentration, or probably more easily, pH plus POH equals 14. If we rearrange that algebraically, we can find out that the POH should be 6.38, and this is acidic and not basic. Sorry, basic and not acidic. Oh boy. Whew. Part B. Again, Kw is 1.0 times 10 to the negative 14th. Rearrange this equation here. Find out what the H plus ion concentration is, because we're given the OH concentration. So the H plus ion concentration is 5.3 times 10 to the negative 13th. Take the negative log of that, and that'll get us the pH. The pH is 12.28. pH plus POH equals 14, so the POH is 1.72. This is also basic. So both A and B are basic.